Pre-calculus, lesson 3.1, exponential functions. So up to this point, we have mainly been talking about polynomial functions, but in this unit, we're going to go ahead and start exploring the next type of functions, transcendental functions, by introducing the exponential. The exponential function f with base b is defined by f of x equal to b to the x power or y equal to bx power, where b is a positive constant other than 1, and x is any real number. So in this case, if we look at our equations, we notice here that x is now in the exponent, and then we're given a base here, b. So anytime where the variable is in our exponent, this is going to be an example of an exponential function. So let's try this out by evaluating. The exponential function f of x equal to 42.2 times 1.56 the x power models the average amount spent f of x in dollars at a shopping mall after x hours. What is the average amount spent to the nearest dollar after 3 hours at a shopping mall? And we notice this is an exponential function because the x variable is in the exponent. So if we look at our variables here, we notice that we're given that x represents hours and f of x is in dollars. So instead of f of x, we can go ahead and find here f of 3 by plugging in 3 for the x value. And so if we go ahead and plug in 3 for our power and plug that all into our calculator, we should get out approximately $160.209, which is about $160. So after about 3 hours at the shopping mall, you've spent about an average of $160. Now let's go ahead and try graphing an exponential function. In this case, we're going to use the x values here of -2, -1, 0, and 1. And so we're going to be plugging these x values in for the variable in the function f of x equal to 3 to the x power. So if we do that, we notice here that we have 3 to the -2 power. Well, remember, negative exponents move our base to the denominator of the fraction. So this would be like 1 over 3 squared, which would be 1/9. Similarly, if we plug in -1, we're going to get out 1/3. 3 to the 0 power is the same thing as anything to the 0 power, or 1. 3 to the first power gives us just 3. I'm going to add 3 squared here, which is 9. So if we go ahead and plot these points, we'll notice that we're going, as we go to the right, we're going up towards positive infinity, but then as we go to the left, our values are getting more and more small, but they're never getting quite to 0. So we're kind of leveling off there towards the x-axis as we go to the left. We're kind of getting this like little growing, increasing graph here. This right here is kind of the basic shape of the exponential function. So let's go ahead and talk about the characteristics of the exponential function. The domain of an exponential function with base b consists of all real numbers. So if you look down here at our curves, the one that we just drew, notice that left arrow is going all the way to the left, the right arrow is going all the way to the right, so it's covering that entire x-axis, giving us the full range of numbers. The range here, though, notice since as to the left, we are getting closer and closer to 0, but not quite reaching it, and then as we go to the right, we kept on going all the way up. This means our range here is going from that 0, because we never quite reach it, all the way up to infinity. Graphs of all exponential functions will pass through the point 0, 1, and that's because anytime we evaluate, it doesn't matter what the base is, anything to the 0 power is 1. So that means here that our y-intercept, no matter what the base is going to be 1. And also this means there's going to be no x-intercept because we're never actually reaching the x-axis. Now, the base, really plays a big part in the shape of our graph. Notice here that if b is greater than 1, then we are going to have a graph that goes up to the right and is increasing, just like the one we did before, the 3 to the x power. This means, though, that if we change the base, where the base is between 0 and 1, so like a fraction, so like 1/3 or 1/2, this means the graph is going to decrease from left to right. And so the smaller the value of b, the steeper the decrease. So we're getting this purple graph here going downward. So if we have a fraction as a base, it's going to be a decreasing graph. But if it is a base greater than 1, it's going to be an increasing graph. A couple other things to know about the exponential function is that it is 1-to-1, so that means it does have an inverse. Okay. And then also, since the graph is getting closer and closer to that x-axis but never touching it, this is going to be an example of our horizontal asymptote. An exponential graph will always have a horizontal asymptote. Now let's go ahead and use the graph that we created of 3 to the x power to help us obtain the graph of the function g of x equal to 3 to the x minus 1 power. So I'm going to go ahead and redraw that 3 to the x power here that we found before here in red. And I'm going to go ahead and graph those points. Notice since that base is 3, it's greater than 1, so it's going to be that increasing graph. And we still have that horizontal asymptote on the x-axis. Now notice here though, then I'm going to go ahead and create another column here and use 3 to the x minus 1. So we're going to be plugging in those same x values here. I'm going to start with 0 since that was our y-intercept. It's usually always easy to start with 0, so we're going to go and continue that. So if I plug in 0 here, I'm going to get out 3 to the negative 1 power, which is going to be 1/3. Notice in this case though, that was the same y value that we got in the original function, but for -1, because it's going to be, we're subtracting 1. Similarly, if I plug in +1, we get out 3 to the 0 power, which is 1. 3 squared, if I plug in 2 there, it's going to subtract 1, so 3 to the first, so we get 3. And so notice all that's happening here is using the previous y value from the previous x value. And so if we actually graph this with these points, we're still getting that increasing graph, which we had saw before, but we might notice here that it looks like the entire graph has just been shifted right 1. That's because if we think back to our transformations, we knew that if we subtracted 1 from the inside, that would be shifting the graph, or in this case, moving it right 1. So the transformations that we learned before with the h and k values, in this case, we can think of this as still holding true for our exponential graphs. So if we added or subtracted a value outside of the function, that would move our graph up and down like our k value. If we had a negative out in front of the base, that would flip it over the x-axis. We had a negative inside the exponent on the x, that would be a flip over the y-axis. And then we also have those stretches and compressions. So those still all hold true. Note here that our horizontal asymptote did not change because the only thing we did here was we shifted right. If we would have shifted up and down, that would have changed our horizontal asymptote. In this case, I'm going to go and write out our general form for transformations using the exponential function. So if I give you the basic form of f of x, where we have a base of b, and then our x in the exponent, well then if we are going to add or subtract inside the exponent, that's going to move us left or right. If I were to add or subtract outside the exponent, that's going to move us up or down. If I added, let's say I had an a value, so remember if we think about a's, if I have an a greater than 1, that's going to be a stretch vertically. But if a was a fraction between 0 and 1, that would be our vertical compression, i.e. making it wider. And then if I put a negative on that a, that will go ahead and flip or reflect over the x-axis. But if I have a negative inside the parentheses, so inside our exponent, that right there would be like a flip or a reflection over the y-axis. So this right here is how it's going to affect our exponential graphs, just like our transformations did before for a quadratic or an absolute value. There's also a very special type of base that we need to talk about, the natural base e. The number e is defined as the value that the quantity 1 plus 1 over n to the n power approaches as n gets larger and larger. So as n is getting closer and closer to infinity, so we're plugging in larger and larger values for n, the approximate value of e to 9 decimal places is going to be about e 2.718281827, so on and so on. It's an irrational number, so it's going to keep on going. But we approximate it to be about 2.72. It's kind of like pi. It's never going to change that. It's always going to be a constant. But e here is what we call the natural base, because it is a value that occurs so often in nature. The function f of x equal to e to the x power is called the natural exponential function. Here's a great example of how to use the base e in an exponential function. We know the function f of x equal to 1066 times e to the 0.042 times x power models the gray wolf population of the Western Great Lakes X years after 1978. Project the gray wolf's population in the recovery area in 2012. Well, notice in this case that we know that f of x is the wolf population and x is years after 1978. And so if we're trying to project the population in 2012, we need to find out how many years are between 1978 and 2012. So if we could do that subtraction between the two, we're going to get out 34 years. So this is the x value we're going to plug into our function. And so if we try to find f of 34, we're going to get that 1066 times e to the 0.042 times 34 power. Notice that e is just going to be that constant. So if you look on your calculator, there is actually an e button. So go ahead and take a moment and find it. It should be close to the second ln button, so natural log, which we'll talk about here soon enough. But if we go ahead and plug in that entire quantity into our calculator, e to the 0.042 times 34 power, multiply that all by 1066, we're going to get out approximately 4,446 wolves. So in 2012, we can predict that this is going to be the population. Another common use for exponential functions is when we're trying to find compound interest. So after t years, the balance A, so the final amount, and account with the principal amount, so the starting amount, and P at an annual interest rate R is given by the following formulas. So we have two different formulas we're going to talk about. The first one is the general one for in compounded periods per year. So like if it's compounded monthly, quarterly, yearly, this is the formula we're going to use. So A is going to be that account or that final amount. We can think of P as the principal or the starting amount. And then we have R, which is going to be our rate, which is usually given to us as a percentage, but we're going to write as a decimal. The T, which is going to be our time, which is going to be years in these problems. And then N is going to be the number of times compounded periods or times per year. So like it was monthly, 12, biannually, 2, daily, 365. Now sometimes, though, we have the special case of where we're compounded continuously. So if we're compounded continuously, this is where we're going to use our second formula here, A equal to P times e to the RT power. So we're going to use that natural exponential base of e, where the P, the R, and the T, and the A all stand for the exact same things before. So let's look at this first problem here. It says a sum of $10,000 is invested at an annual rate of 8%. Find the balance in the account after 5 years subject to quarterly compounding. So key here is that we have compounded quarterly. That means we need to use our 1 equal to P times 1 plus R over N to the N times T power. And so let's go through the problem here and kind of pick out what each of our variables are going to be. Since we're starting out with $10,000, that's going to be our principal amount. The rate here was 8%, so we need to write that as a decimal by moving the decimal place 2 places to the left, giving us 0.08. And then since we're waiting 5 years, that's going to be our time. And since it's quarterly, there's 4 quarters in a dollar, so 4 quarters in a year. And so that means the N here is going to be 4. If we go ahead and plug these all into our equation then, since we're solving for A, we're trying to find how much money was left over. We're going to get 10,000 times 1 plus 0.08 over 4, all raised to the 4 times 5 power, which we're going to simplify that base first. So the 1 plus 0.08 over 4 gives us 1.02, and then all raised to the 20th power. So we plug into our calculator, we're going to get out approximately $14,859.47 after 5 years in this account, if we're compounded quarterly. But what if we were to compound it in a different way? What if we were going ahead and try doing continuous compounding here? Well, let's go ahead and find out that amount. In this case, since it's compounded continuously, that means we're going to have to use our other formula with the base E. Our P here is still going to be the same of $10,000. The R will still be that 0.08. And since we're still using the same amount of time, we're going to use you're going to use 5. But since it's compounded continuously, this is going to be where we use E. And so if we go ahead and plug these all into our equation, we're going to get 10,000 times e to the 0.08 times 5 power. Remember that e is still just that 2.72 that we've used before, but just use the e button on your calculator. And if we go ahead and plug that in, we're going to get out approximately here $14,918.25, which if we think back, that was more than compounded quarterly, which makes sense because if I'm getting compounded more often, that means I'm getting paid more.